Welcome to this exciting problem walkthrough. In this video, we'll explore problem number 1924, the number of ways to wear different hats to each other. We'll break it down step by step, analyze different approaches, and uncover the most efficient solution. Let's dive right in. In this problem, we are tasked with assigning hats to people in a way that satisfies their preferences. Specifically, we have n people and 40 hats labeled from 1 to 40. Each person has a subset of these hats that they prefer, and our goal is to determine the total number of ways to assign hats such that each person gets exactly one hat they prefer, and no two people share the same hat. Since the number of possible assignments can be very large, we will return the result modulo 10⁻9 plus 7. The input is given as a 2D list, where each sublist represents the preferences of a specific person. The output is a single integer representing the total number of valid assignments. Let's look at some examples to clarify this further. Consider the first example, where the input preferences are hats equals 3, 4, 4, 5, 5. Here, we have 3 people, person 0, person 1, and person 2. Person 0 prefers hats 3 and 4, person 1 prefers hats 4 and 5, and person 2 prefers hat 5 only. The challenge is to assign unique hats from their preferences to each person. After evaluating the possibilities, the only valid assignment is to give hat 3 to person 0, hat 4 to person 1, and hat 5 to person 2. This is the only configuration that satisfies the constraints, so the output for this example is 1. Now let's examine another example with the input hats equals 3, 5, 1, 3, 5. This time, we have 2 people, person 0 and person 1. Person 0 prefers hats 3, 5, and 1, while person 1 prefers hats 3 and 5. We need to find all valid assignments of hats where each person gets one hat from their preferences, and no two people share the same hat. There are 4 valid assignments, person 0 can take hat 3 and person 1 can take hat 5, or vice versa. Alternatively, person 0 can take hat 1, leaving person 1 with either hat 3 or hat 5. This gives us a total of 4 valid assignments, so the output here is 4. In a more complex example, let's consider hats equals 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Here, we have 4 people, and every person prefers all 4 hats. This scenario is equivalent to finding the number of permutations of 4 hats among 4 people, as each person can be assigned any of the 4 hats without restriction. The total number of permutations of 4 items is 4, which equals 24. Therefore, the output for this example is 24. Finally, let's consider some edge cases. In the minimum input scenario, where n equals 1 and the first person has only one preferred hat, there is exactly one valid way to assign the hat. For example, with hats equals 1, the output is 1. At the other extreme, for the maximum input scenario with n equals 10 and all people preferring all 40 hats, the number of valid assignments becomes extremely large, requiring an efficient approach such as dynamic programming to compute the result. Other cases include situations with no overlap in preferences, where the result is simply the product of individual preferences, and cases where all preferences overlap, which reduces to the number of permutations of n hats. Lastly, for all outputs, we ensure the result is returned modulo 10⁻9 plus 7 to handle large numbers efficiently. To solve this problem, we first explored the brute force approach. This method generates all possible permutations of hat assignments for the given number of people, ensuring that each person is assigned a hat from their preferred list without any 2 people sharing the same hat. While the idea is straightforward, the number of permutations grows factorially with the number of hats, making it computationally infeasible. For instance, with 40 hats, the number of permutations reaches 40 factorial, which is an astronomically large number, even when the number of people is small. Next, we considered backtracking, which assigns hats recursively. This method avoids generating all permutations by trying to assign hats person by person, ensuring validity at each step. However, this approach still suffers from exponential complexity because each person has up to 40 choices, leading to a worst-case time complexity of 40 raised to the power of n. Finally, we arrived at the dynamic programming approach combined with bit masking. This strategy uses a DP table to track valid assignments efficiently, drastically reducing the computational cost.
By focusing only on valid state transitions, this approach avoids the inefficiencies of the previous methods while remaining feasible for the given constraints. The dynamic programming approach with bit masking relies on a few key observations. Each person's assignment can be tracked as a bit in a mask, where the mask represents which people have been assigned hats. The state transition involves adding a hat to a person's assignment, but only if that hat is in their preferred list and hasn't already been assigned to someone else. The DP table, DP, mask, I, represents the number of ways to assign hats to the subset of people defined by mask, using hats only from the first I hats. The final result is stored in DP, 1n, 1, 40, where 1n, 1 is the bit mask representing all n people being assigned hats. The time complexity of this approach is 40*2 to the power of n, where 40 accounts for the total number of hats and 2 to the power of n covers all possible subsets of n people. This is efficient for up to 10 people, which aligns with the problem's constraints. The dynamic programming strategy is chosen because, compared to brute force and backtracking, it significantly narrows the search space while maintaining clarity and scalability. The linear dependency on the number of hats ensures it remains practical for the fixed set of 40 hats in this problem. When comparing the different strategies, we see clear trade-offs. The brute force approach is conceptually straightforward but completely infeasible due to its factorial growth and complexity, which renders it unsuitable for any meaningful input size. Backtracking improves upon brute force by pruning invalid assignments as it progresses, but it still suffers from exponential complexity, which makes it impractical for larger values of n. The dynamic programming approach with bit masking strikes the right balance between efficiency and scalability. By focusing only on valid state transitions, it reduces the computational overhead significantly while keeping the implementation manageable. Its time complexity, 40*2 to the power of n, fits within the problem's constraints, making it the optimal choice for handling up to 10 people and 40 hats. This approach is not only efficient but also well-suited to the fixed number of hats, ensuring that both time and space complexities remain under control. Thus, dynamic programming with bit masking is the clear and most effective strategy for solving this problem. To solve this problem, we need to assign unique hats to each of the n people, ensuring that each person only receives a hat from their list of preferences. The challenge lies in finding the total number of valid assignments where no two people share the same hat. To begin, we represent the input as a dictionary or list of lists, where each person's preferences are stored. For instance, if person 0 prefers hats 1, 2, and 3, person 1 prefers hats 2 and 3, and person 2 prefers hats 3 and 4, our input would look like this: preferred equals 1, 2, 3, 2, 3, 3, 4. Next, we define states using dynamic programming. Here, a bit mask is used to track which people have already been assigned hats. With n people, the bit mask ranges from 0, meaning no one has been assigned, to 1n, 1, meaning all n people have hats. The DP state, DP, hat, mask, will represent the number of ways to assign hats 1 through the current hat such that the bit mask indicates which people already have hats. This setup forms the framework for our solution. The first step in building the DP solution is to define the base case. When no hats are considered, meaning hat equals 0, the only valid assignment is the empty assignment. This means DP 0, 0 equals 1, and for all other masks, DP 0 mask equals 0. From here, we define the transition function. For each hat, there are two possibilities. First, we can choose not to assign the current hat to anyone. In this case, the number of valid assignments remains the same as DP, H1, mask, where H is the current hat. Second, we can assign the current hat to a person. For each person who prefers this hat and hasn't yet been assigned one, we update DP, H, mask, 1p, by adding DP, H1, mask. This ensures that the new state reflects the addition of this person and their hat assignment. The transition equation captures this as DP, H, mask, equals DP, H1, mask, plus the sum of DP, H1, prev underscore mask, for each person P where P prefers the current hat, has not been assigned a hat, and prev underscore mask is the state before assigning the hat. Finally, the result is stored in DP, 40, 1n, 1, representing all 40 hats considered and all n people assigned. To optimize this approach, we take advantage of the problem constraints. While the theoretical limit involves iterating over all 40 hats and 2 to the power of n states,
we only need to focus on hats that appear in at least one person's preference list. This reduces unnecessary computations significantly. Additionally, edge cases must be handled carefully. For instance, if no valid assignment exists, such as when preferences don't overlap at all, we should return 0. Another edge case arises when the number of people exceeds 40, making it impossible to assign unique hats, in which case we also return 0.
Dynamic programming is an ideal choice for this problem due to the overlapping subproblems.
Partial assignments for the same subset of people with fewer hats can be reused efficiently. The bitmask representation plays a crucial role here, as it allows us to track assigned people using a compact and efficient encoding. For n people, this representation has a size of 2 to the power of n, which is manageable for small values of n overall. This approach balances efficiency and scalability within the problem's constraints. The algorithm's scalability depends on the constraints of the problem. For relatively small n, such as up to 10 people, the algorithm performs well even with 40 hats. Pruning irrelevant states further enhances efficiency by ensuring we only compute transitions for hats that are relevant to at least one person's preferences. The data structures used in this solution are straightforward yet effective. The DP table, represented as a 2D array, stores the number of valid assignments for each combination of hats and bitmask states. This table has dimensions of 40 by 2 to the power of n, reflecting the number of hats and states we need to consider. Additionally, the preference list is stored as a dictionary or list of lists, making it easy to access each person's preferred hats. Bitmask operations, such as setting or checking bits, are performed efficiently using bitwise operators like OR, and left shifts. These operations allow us to update and check states in constant time, which is critical for maintaining the algorithm's overall efficiency. Finally, let's analyze the complexity of this solution. The time complexity is driven by iterating over 40 hats and 2 to the power of n masks, with transitions proportional to the average number of hats each person prefers. In the worst case, this results in a complexity of 40 times 2 to the power of n times m, where m is the average number of preferences per person. For space complexity, the primary cost comes from storing the DP table, which requires 40*2 to the power of n space. While these complexities may seem daunting, they are manageable for small n, such as 10 or fewer people, due to the constraint of at most 40 hats. By focusing on relevant states and leveraging the efficiency of bitmask operations, this approach balances computational feasibility with the problem's requirements, making it both practical and optimized for the given constraints.
In this implementation, we start by importing the ru_cache decorator from Python's functools module.
This will allow us to optimize our recursive function by caching results for previously computed states. We define a class solution with a method numberWays, which takes a list of lists as input, where each sublist represents the hats liked by a specific person. To handle large outputs, we define a constant mod set to 10 to the power of 9 plus 7, as we'll need to return the result modulo this value. Then, we calculate the number of people, n, from the input. Next, we prepare a mapping of hats to the people who like them. This is stored in a dictionary hat_to_people, where each key corresponds to a hat number between 1 and 40, and the value is a list of people who have that hat in their preferences. For each person and their list of liked hats, we populate this mapping to efficiently look up which people like a given hat. Now, we define the recursive function dp, which will use bitmasking to track which people have already been assigned hats. The function takes two parameters, hat, which is the current hat number being considered, and mask, an integer representing the assignment state of the people as a bitmask. We use the ru_cache decorator to memoize the results for each unique combination of hat and mask. The base case for the recursion checks if all 40 hats have been considered, and if the bitmask represents that all people have been assigned hats, it returns 1, otherwise, it returns 0. The recursive logic starts with skipping the current hat, which calls dp with the next hat number and the same mask. Then, we iterate through the list of people who like the current hat. If a person hasn't been assigned a hat yet, we update the mask to include this person and make a recursive call to consider the next hat. Within the loop, for each person who can be assigned the current hat, we calculate the total number of ways by adding the result of the recursive call with the updated mask. Since the result can grow very large, we take the modulo of mod at each step to ensure the value remains manageable and within the constraints of the problem.
This modular arithmetic is crucial for preventing integer overflow and for meeting the requirements of the problem statement.
Finally, the dp function returns the number of ways to assign hats to people, considering all combinations from the current state. To solve the problem, we initiate the recursive process by calling dp1, 0, starting with the first hat and an empty bitmask.
This represents that no hats have been assigned yet.
The result of this function call, which is the total number of valid assignments, is then returned by the numberWays method. This completes the implementation, and the use of bit masking along with memoization ensures that the solution is both efficient and optimal for the given constraints. Here, we begin by importing the necessary libraries and defining our solution class.
We also declare a constant mod, set to 1,000,007,000, which will be used to handle large numbers during modular arithmetic.
The main method, numberWays, takes a list of lists, where each inner list represents the hats that a specific person likes. We determine the number of people, n, based on the size of this input list. Next, we create a mapping of hats to the list of people who like each specific hat. This is represented as a list of lists, where each index corresponds to a hat, and its value is a list of people who like that hat. We initialize this structure for all 40 hats, and then populate it by iterating through each person and their preferences. Finally, to optimize our solution, we set up a 2D array called dp for memoization, where the rows represent hats and the columns represent bitmask configurations of assigned people.
Each cell is initialized to -1 to indicate that it hasn't been computed yet. The numberWays method concludes by invoking the dfs function, which is our recursive helper method.
This function takes several parameters, the current hat being considered, the current bitmask representing which people have been assigned hats, the total number of people, the hat-to-people mapping, and the memoization table. Within DFS, the base case checks if all hats have been processed. If so, it returns 1 if all people have been assigned hats, or 0 otherwise. To avoid redundant calculations, we check if the current state has already been computed in the DP table and return the cached result if it exists. We then calculate the number of ways by first skipping the current hat and recursively processing the next. Additionally, for each person who likes the current hat and hasn't yet been assigned one, we try assigning this hat to them. This updates the bitmask and recurses to the next hat. After processing all possibilities, the result is stored in the DP table and returned, ensuring modular arithmetic is applied to prevent overflow.
Finally, we close the dfs function and the solution class.
With this implementation, the recursive calls efficiently explore all valid combinations of hat assignments, leveraging memoization and bitmasking to ensure optimal performance. This approach systematically considers each hat in person, ensuring that the constraints are met while avoiding redundant computations. To solve this problem, we begin by initializing some key variables. First, we set mod to 10 to the power of 9 plus 7, which helps us manage large numbers by keeping results within bounds.
Since there are 3 people, we set n to 3.
Additionally, we create a mapping called hat_to_people, where each key represents a hat number from 1 to 40, and the corresponding values are lists of people who like that hat.
Next, we map hats to people based on their preferences.
Person 0 likes hats 3 and 4, so we update hat_to_people such that hat 3 maps to 0, and hat 4 also maps to 0. Similarly, person 1 likes hats 4 and 5, so hat 4 now maps to 0, 1, and hat 5 maps to 1. Finally, person 2 likes hat 5, so we update hat 5 to map to 1, 2. Now, for the dynamic programming approach, we define dp, hat, mask, where hat represents the current hat being considered and mask is a bitmask indicating which people already have hats. For example, if hat equals 1 and mask equals 0, 0, 0, it means no one has a hat yet, and we skip this hat to move to the next case by calling dp 2, 0, 0, 0. In the next case, when hat equals 2 and the mask is still 0, 0, 0, we again skip hat 2 and proceed with dp 3, 0, 0, 0. However, for hat 3 with mask 0, 0, 0, we see that person 0 can wear this hat. So, we assign hat 3 to person 0, represented by dp 4, 0, 0, 1, where the mask 0, 0, 1 indicates person 0 now has a hat. Alternatively, we could skip hat 3 and call dp 4, 0, 0, 0 to explore other options. For hat 4, with mask 001 indicating that person 0 already has a hat, person 1 can wear this hat. Assigning hat 4 to person 1 results in DP 5011, where the mask 011 shows persons 0 and 1 both have hats. We can also skip hat 4 and call DP 5001. Finally, when considering hat 5 with mask 011, meaning persons 0 and 1 have hats, person 2 can wear hat 5. This is represented by DP 6111, where the mask 111 indicates that all 3 people now have hats. Alternatively, we could skip hat 5 and call DP 6011. The base case for our dynamic programming approach occurs when the hat number exceeds 40. At this point, we check whether all people have hats by verifying if the mask equals 111. If it does, we return 1, indicating a valid assignment. Otherwise, we return 0. In this example, we find there are 4 total ways to assign hats to people: 3, 4, 5, 3, 5, 4, 4, 3, 5, and 4, 5, 3. Moving on, let's consider another example. Here, all 3 people like hats 1, 2, and 3, so our hat _to_ people mapping will have hats 1, 2, and 3 each mapping to 0, 1, 2, while the rest of the hats map to empty lists. We again proceed with dynamic programming to calculate the total number of valid assignments. To solve this example with dynamic programming, we start with hat 1 in mask 000, meaning no one has a hat yet. Here, person 0 can wear hat 1, leading to DP 2001. Similarly, person 1 can wear hat 1, resulting in DP 2010, and person 2 can wear hat 1, giving DP 2100. Alternatively, we can skip hat 1 and call DP 2000. Next, for hat 2 with mask 001, indicating that person 0 already has a hat, person 1 can wear hat 2, resulting in DP 3011. Person 2 can also wear hat 2, leading to DP 3101. If we skip hat 2, we call DP 3001. For hat 3 with mask 011, meaning persons 0 and 1 already have hats, person 2 can wear hat 3, resulting in DP 4111. Alternatively, we can skip hat 3 and call DP 4011. The base case checks if the hat number exceeds 40, and if the mask equals 111, we return 1. Otherwise, we return 0. In this example, we calculate that there are 6 total ways to assign hats to people. These correspond to all permutations of hats 1, 2, and 3 being assigned to persons 0, 1, and 2. Finally, let's consider one more example where the preferences for each person are distinct. Person 0 likes hat 1, person 1 likes hat 2, and person 2 likes hat 3. This creates a straightforward hat _to_ people mapping where hat 1 maps to 0, hat 2 maps to 1, and hat 3 maps to 2, while the rest of the hats map to empty lists. We then approach this problem using dynamic programming as before. For this final example, we start with hat 1 in mask 000, meaning no one has a hat. Person 0 can wear hat 1, resulting in DP 2001, or we can skip hat 1 and call DP 2000. For hat 2 with mask 001, indicating that person 0 already has a hat, person 1 can wear hat 2, leading to DP 3011. Alternatively, we can skip hat 2 and call DP 3001. Finally, for hat 3 with mask 011, meaning persons 0 and 1 already have hats, person 2 can wear hat 3, resulting in DP 4111. We could also skip hat 3 and call DP 4011. The base case checks if the hat number exceeds 40, and if the mask equals 111, we return 1. In this case, there's only one valid assignment, 1, 2, 3, so the total number of ways is 1. The time complexity of this solution is rooted in the dynamic programming approach we use. First, let's consider the number of states. The DP function is defined with 2 parameters, hat, which ranges from 1 to 40, and mask, a bit mask that represents which of the n people have already been assigned hats. Since there are 40 hats, the first parameter has 40 possible values. Meanwhile, the mask parameter, because it's a bit mask representing subsets of n people, has 2n possible values. This means the total number of states in our DP table is 40*2n. Moving to the cost of computing each state, for a given hat, mask, pair, we calculate the number of ways by either skipping the current hat or assigning it to one of the people who like it. If k represents the average number of people who like a given hat, the computation involves iterating through these k people, making the cost per state proportional to k. Now, to calculate the total time complexity, we multiply the number of states, 40*2n, by the cost per state, which is proportional to k. This gives us a total time complexity of 40 times 2 to the power of n times k. In the worst case, where every person likes every hat, k becomes equal to n, resulting in a worst-case complexity of 40 times 2 to the power of n times n. Since 40 is a constant, it doesn't affect the dominant factor, so the overall time complexity simplifies to 2 to the power of n*n. Turning to the space complexity, we first consider the recursive call stack. The depth of recursion is limited to 40, as each recursive call corresponds to a specific hat. Therefore, the space used by the stack is 40, which is constant. Additionally, we have the memoization table, which stores results for all hat, mask, pairs. Since there are 40*2n states and each state stores an integer, the space required for memoization is 40*2 to the power of n. When we combine the space requirements of the recursive call stack and the memoization table, the total space complexity is dominated by the memoization table, resulting in 2 to the power of n. To better understand the efficiency of this approach, let's compare it to a naive, brute force solution. A brute force method would involve generating all possible assignments of hats to people and verifying if each assignment satisfies the preferences. This would result in n permutations for n people, and for each permutation, we would need to check the preferences, leading to a time complexity of n*n. In contrast, the dynamic programming approach significantly reduces the complexity to 2 to the power of n*n by using bit masking and memoization to avoid redundant calculations. This makes it exponentially faster for larger values of n. The mathematical proof of this complexity stems from the fact that we only process 40*2n states, and each state takes constant time proportional to k to compute. To fully understand the performance, let's analyze the best, average, and worst cases. In the best case, when each person likes only a few hats, the average value of k is much smaller than n. This reduces the time complexity to 2 to the power of n*k, where k is significantly less than n. In the worst case, where every person likes every hat, k equals n, and the time complexity becomes 2 to the power of n*n. For the average case, we generally find that k is smaller than n in practical scenarios, meaning the execution is typically faster than the worst case bound. This breakdown highlights how the dynamic programming approach effectively handles the problem's combinatorial nature while minimizing unnecessary computations. A common issue when solving this problem is misinterpreting the constraints, particularly the assumption that the number of people n is always small. This often leads to brute force solutions, like generating all possible permutations, which have factorial complexity. For example, calculating permutations for 40 hats results in an 40 complexity, which is computationally infeasible. Another mistake is not accounting for overlapping subproblems in dynamic programming. If we fail to cache intermediate results, we end up solving the same subproblems repeatedly, which drastically increases runtime and can lead to exponential complexity. Similarly, incorrect base cases in recursive solutions can cause infinite recursion or incorrect outputs. Base cases act as the termination condition, and if they're improperly defined, the entire recursion falls apart, either looping endlessly or returning wrong results. Another common pitfall is ignoring edge cases, such as when n equals 0, meaning there are no people, or when certain hats are unavailable. Neglecting these scenarios often results in runtime errors or incorrect outputs. Additionally, hard-coding solutions for small inputs can be problematic. While it might be tempting to write code that handles specific test cases, these solutions don't generalize well. For instance, code that works for n equals 2 might fail for larger values or unexpected inputs. This lack of generalization is a frequent failure point in interviews in competitive programming, where robustness and scalability are critical. When approaching this problem in an interview, it's important to start by breaking down the problem.
Determine if it can be framed as a combinatorial problem, a graph traversal, or a dynamic programming challenge, and make sure to articulate your thought process clearly. Once you have the basic understanding, optimize step by step. Begin with a brute force solution to establish the foundation, and then refine it by identifying patterns or redundancies. For larger constraints, like handling up to 40 hats, bit masking can be a powerful tool. It allows you to efficiently encode subsets, reducing both space and time complexity. Also, take the time to communicate trade-offs in your approach. For example, you might explain why you chose dynamic programming over a graph-based method. Lastly, don't forget to test edge cases, such as when n equals 0, n equals 1, or when specific hats are already taken, to ensure your solution is robust. This problem shares similarities with several others on LeetCode. For instance, problem 1434, number of ways to wear different hats to each other, is directly related, as it also involves assigning hats to people under specific constraints. Problem 526, beautiful arrangement, involves permutations with constraints, much like this problem. On the other hand, problem 198, house robber, is a simpler dynamic programming problem that highlights the importance of optimizing overlapping subproblems. Lastly, problem 1723, find minimum time to finish all jobs, deals with the optimal assignment of tasks using techniques like backtracking and dynamic programming, which align with the strategies used here. Exploring these problems can deepen your understanding of the underlying concepts and techniques. There are several approaches to solve this problem, each with its own trade-offs. The brute force method involves generating all permutations of hat assignments and filtering the valid ones. While straightforward to implement, this approach is highly inefficient, with a time complexity of 40. A better option is dynamic programming with bit masking, where the DP array stores the number of ways to assign hats based on the current mask of assigned hats. This approach is much more efficient, with a complexity of n*2 to the power of n, but it requires a solid understanding of bit masking and state transitions. Another alternative is backtracking with pruning, where you recursively assign hats to people and backtrack when constraints are violated. This method is easier to implement than dynamic programming but tends to be slower for larger inputs. Understanding these trade-offs helps you choose the best approach based on the problem's constraints and requirements. Great job following along. To recap, we discussed the problem, analyzed different approaches, and highlighted key takeaways. Remember, practicing problems like this helps sharpen your algorithmic thinking. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!